Hello, I'm Tim Weaving, a PhD student at University College London, and I'm pleased to welcome you all to the 29th instalment in CompBioMed's e-seminar series in collaboration with the Virtual Physiological Human Institute, or VPHI. This project is funded via the EU Horizon 2020 Research and Innovation Programme with grant number 823712, for which we are very grateful. Now, the talk today is titled OpenMP in the Exascale Era and will be given by Dr. Mark Bull, a senior research fellow at the Edinburgh Parallel Computing Centre, whose research interests include benchmarking, parallel algorithms, parallel programming APIs, and novel uses of high-performance computing. Mark acts as EPCC's representative on the OpenMP Architecture Review Board and is a former chair of the OpenMP Language Committee. Before we begin, I'd like to briefly remind you that the session is being recorded and will be available on the CompBioMed website and YouTube channel shortly. So please do use this to go back over parts of today's talk and others in the series, and then maybe even share these e-seminars with your friends and colleagues. There's going to be a Q&A session at the very end of the talk today, so please save your questions until then. Once the talk is finished, you can post your questions in the Ask the Staff a Question panel, which is accessible via the question mark icon on your screen, and I will then read your questions out to Mark to keep the session running smoothly. Now, that's enough from me. I very much hope that you enjoyed today's talk. And finally, Mark, please feel free to take it away.
Thank you very much, Tim, and thank you very much for the invitation to give this e-seminar today. So what I'm going to talk about is, well, very briefly, for those of you who might not be familiar with it, say a little bit about what OpenMP is, and then discuss why OpenMP might be relevant for large-scale or exascale computing. And dive into some of the more technical topics and talk about hybrid MPI and OpenMP programs. Talk about OpenMP for programming GPUs and using OpenMP tasks for irregular parallelism, and then end up saying a little bit about why you might want to use OpenMP and not some other API. Because OpenMP is a good thing, but it's not perfect, and there are some other alternatives which are worth considering. Okay, so let's start off by thinking about what is OpenMP. So OpenMP is an API which is designed for programming shared memory parallel computers. And it consists of a set of extensions to Fortran, C, and C++. So those are the three base languages which OpenMP supports. And these extensions consist mostly of compiler directives. But there's also some runtime library routines and environment variables that are part of the standard. So OpenMP is an open standard, and it's administered by a body called the OpenMP Architecture Review Board, which consists of now over 30 members from member institutions coming from industry, academia, and government labs. Of which EPCC here at the University of Edinburgh is one of them. So OpenMP has its own website, which you might want to explore a bit, but the main useful thing that you can find there is to actually be able to download the specifications and examples documents, which you can get from there. OpenMP is quite old now. The original standardization process started in the mid-1990s, so it's well into its third decade now. So for anybody who isn't already familiar with OpenMP, this is a very simple example to illustrate what it looks like. So suppose we have a loop nest in C like this, which has independent iterations. So it doesn't matter in what order we execute the iterations of those loops. Then we can put an OpenMP directive on top of that, And essentially what that says is create some threads and then distribute the iterations of the outermost loop, in this case, the I loop, over those threads. By default, it'll split those iterations as equally as possible between the threads and execute them in parallel. Now, OpenMP is actually a big standard. It's much more than just parallelizing loops, but in practice, this is by far the most commonly used feature in scientific applications, is to execute loops in parallel like this. Obviously, there's a bit more to it than that, but this is kind of this is a simple example and the basic idea. So why might OpenMP be relevant for exascale or at least very large scale computing? Well, good question, because large scale HPC systems are not shared memory systems. They are composed of lots and lots of nodes where each node has its own memory. And traditionally, we've usually programmed distributed memory systems like this using a message passing library. And in practice, that's almost always MPI. There are a few other niche possibilities, but almost all large-scale applications use MPI as the basic parallel library, which works for cross-distributed memory. So, what's the role of OpenMP? Well, two things really. OpenMP can be used to exploit multi-core nodes more efficiently. So these days, the nodes that we're building large systems out of have lots of cores in them, and there is shared memory inside a node. And it also allows us to program GPUs with a high-level and vendor-neutral API. So we look at exascale systems and how they're architected. So recent trend has been to build more powerful systems, essentially by adding more cores per node. So just increasing the core count. The core count on chips has been increasing. So we're now seeing chips with 64 cores, soon be 128 cores, that sort of scale. And also by adding GPUs. So this can be multiple GPUs per node, maybe 4 or 8 GPUs per node is technically feasible and possible and sensible. But these systems have not gained power so much by adding more nodes. Okay, so it's really the power of the node that's increasing rather than the node count. So for example, if you look at the last two national supercomputer systems that we've had in the UK. So the previous one was Archer, which was in operation until 2021. So that had just under 5,000 nodes with 24 cores per node. And the current system, Archer 2, has, well, a few more nodes, but so roughly 5 times as many cores per node. And then if we look at Frontier, so the first true exascale system in the US, then that has order of 9,000 nodes, but those gain their power by having 64 cores and 4 GPUs per node. So the first way that OpenMP is useful for large-scale systems and large-scale applications is to use hybrid MPI and OpenMP. So this is to use both MPI and OpenMP APIs in the same application code. So the MPI provides the parallelism across different nodes, and OpenMP exploits shared memory parallelism inside the node. And this style of application is becoming increasingly common on HPC systems. So that can be useful both to reduce memory usage and or to improve the scalability of the application. And I'll look a little bit more in detail about why that is and how that works in a moment. The nice thing is that although MPI and OpenMP were never designed to work with each other together, they were both developed independently as APIs long before this type of system existed. The semantics are actually pretty straightforward. It's pretty clear what it all means, particularly if we stick to the style of programming where there are no MPI calls inside OpenMP parallel regions. And so if all the MPI is done in the part of the OpenMP code that is sequential, then everything is very straightforward. We're not restricted to doing that. If we do MPI from inside parallel regions, things get a little bit more complicated. At some point, we might have to care about whether our MPI library is thread safe or not, and how that impacts performance. But otherwise, it all works pretty well. However, this does introduce another problem. We need then to choose how many OpenMP threads we're going to run per MPI process. And it turns out to do with reasons of scalability inside the node and hardware features like non-uniform memory access regions, that running just one MPI process per node is typically not the best solution. We typically need to run more than one MPI process per node for maximum performance. And the performance then becomes, when we do this tuning of how many threads per process we run, then the performance is actually a fairly complicated trade-off between multiple sources of overhead. And it's actually quite difficult to identify optimization opportunities without doing some very, very careful performance analysis and profiling. But that can be done. In practice, people often just make the choice by experiment and do a few test runs and figure out how many threads per process to run. So what are the potential advantages of programming like this compared with using just MPI everywhere? So MPI everywhere is generally workable. And that's been the style of programming that's been common for the last 30 years, I suppose, really. So what are the potential advantages of mixing MPI and OpenMP? The first one is actually nothing to do with performance. It's actually to do with reducing the memory usage. So there are, because for every MPI process we have, we may have copies of some replicated data structures. And that's true even if we have some domain decomposition scheme. We have some replication of data typically in halo regions. But there's also data that there's internal data that's consumed by the MPI library, which also contributes to the memory usage. So having fewer MPI processes and having OpenMP threads share the data inside a process can help to reduce the overall memory usage of the application. And that's often critical, even just to be able to fit an application run for a particular data set in a given number of nodes. The other advantages are all to do with performance. The next one is that OpenMP allows us a reasonably easy way of exploiting some additional levels of parallelism. So we find that with quite a lot of MPI applications, the way that they were originally designed, the parallelism that's exploited by the MPI parallelism is limited in extent just by the nature of and that's often limited by the nature of the scientific problem rather than actually the scalability of the code. And And it turns out that it's often easier to do that exploitation of the additional of lower levels of parallelism to get more scalability. It's easier to do that by adding OpenMP than by trying to do that in the original pure MPI code. In principle, there's no real reason why you shouldn't do it all in MPI. It just turns out to be easier because it requires less re-engineering of the application. Next possible reason is that it actually reduces computation. So some MPI codes will replicate some parts of the computation just because it's convenient and because it actually may be less expensive to replicate that computation everywhere rather than, say, have one process do it and then communicate the results to all the other processes. So there can be some cases where you actually end up doing less computation. Another example would be where you have some replicated computation in halo regions, for example. Fourth good reason is to reduce load imbalance. So if we have codes where load balancing between MPI processes is a problem, then it turns out it's often easier and less expensive to balance load between threads in OpenMP than it is to do it between processes in MPI. Whenever we load balance in MPI, we not only have to decide where to move computation, we also have to explicitly move the associated data with it. And the complexity and cost of doing that may eventually limit the scalability. So it can be good if we have tricky load balance problems. It can be good to keep the number of MPI processes low and exploit other parallelism with threads instead, which is easier to load balance. And the final reason is the ability in some cases to reduce the communication costs. So for example, don't communicate data that isn't being used. Some MPI applications, just for ease of design and implementation, actually communicate more data than is necessary, simply because you often don't know at runtime what data your neighboring processes are actually going to need. So that's one reason. We also end up with fewer MPI ranks in collective communications, and also end up with fewer and possibly larger point-to-point messages. So that's in a sense is beneficial because we're reducing every message comes with some latency overhead, so we can avoid some of that. So we think about what happens. So suppose we do an experiment where we have an application and we keep the total amount of hardware fixed. So we're thinking about fixing the number of cores that we're going to use and then varying the number of threads per MPI process. So we're going to increase the number of threads per MPI process and correspondingly reduce the number of MPI processes so that the product of the two numbers is always equal to the total number of cores that we're using. Then, very typically what we find is that the total time that we spent in the MPI library doing communication tends to go down. We tend to get less load imbalance between processes, and we also tend to, in some cases, to reduce the amount of computation. On the other hand, we find that as we increase the number of threads, the amount of time that threads are idle tends to increase. The cost of synchronizing threads increases. The way OpenMP is designed is that it encourages you to write code which includes a lot of barrier synchronization. So for example, at the end of every parallel loop in OpenMP, by default, there's a full synchronization point built between all the threads. And also, we may also run into the problem that the load imbalance between threads might increase. So we might just transfer if we're not careful, we might just transfer load imbalance between processes interloading balance between threads. And the other thing that tends to go wrong is that the way that the code uses the memory system may get less efficient. So we become subject to memory system effects like false sharing and non-uniform memory access effects. So I'm going to show you a couple of examples of experiments like this. So these were run on Archer 2. So this is a HP Cray EX system. It has 2 AMD Rome processors. So each of those has 64 cores in a node. So that's 128 cores per node, which share memory. This system is a little bit complicated in its memory hierarchy. There are actually 4 NUMA regions per socket. So there's 1 NUMA region, so 1 separate memory region per physical memory region for every 16 cores. And there's also a shared level 3 cache between every 4 cores. So it's a slightly messy and complicated memory design. And this system uses the HP Cray proprietary slingshot network. Okay, and so first example I'm going to look at is a code called Castep, which is a density functional theory package. So this is for electronic structure calculations, so quantum chemistry basically. So here what I'm showing is the let me get a pointer up here. Okay, so what I'm showing is the execution time. Okay, so small is good versus the number of nodes. So remember, we've got 128 cores per node, and we're using all those cores. And then what happens if we vary the number of threads per MPI process? So the dark blue bars are 1 thread per process. So that's effectively equivalent to pure MPI, and then 2, 4, 8, and 16. So look at the dark blue bars, what we can see is that the scalability of the pure MPI version actually runs out after 4 nodes. So when we go to 8 nodes, the code starts getting slower again, and then 16 nodes, still slower again. But if we go to, for example, 4 or 8 threads per MPI process, then what we find is that the code keeps scaling to 8 and eventually 16 nodes. We actually get some really useful performance benefits by the time we're at the sort of close to the scalability limit, which is for this particular example is around 8 or 16 nodes. So we look a bit more carefully into what's actually going on here. Why do we see these benefits? Well, if we break down do some profiling and break down the execution time into different components, then we can have some better understanding of why that happens. So the important components here are the blue one, which is actually computation. Okay, so doing useful computation. The purple one is time spent in MPI collectives, and in this case, it's because this code relies heavily on FFTs. This is mostly MPI all-to-all communication. And then the third important one is the red category. So this is time where the OpenMP threads are idle, doing nothing. And in this case, it's because this is while the code is doing the FFTs, that's a single threaded library in this case. So while the FFTs are going on, all the other threads, all the other OpenMP threads are sitting around doing nothing. But we can see what happens is as we go from 1 thread per process to 2 threads per process, we get a big saving, particularly in the amount of time spent in collectives. And we also get some reduction in the computation, and that's the computation. That's some of the computation inside the FFTs is also reduced. But to partly compensate, we also find that we also have a significant amount of time where threads are doing nothing. And we can see that this this trend continues, that eventually by the time we get to 16 threads per process, we've reduced the number of MPI processes so much that the MPI collectives are almost nothing now, but we now have a lot of thread idle time. So for this particular configuration, it turns out that 4 threads per MPI process is the best. And another example is a proxy application, it's a mini application called CoMD, which is classical molecular dynamics. So this is a scheme which is, it's pretty straightforward molecular dynamics with a link cell scheme rather than a neighbor list scheme. And again, if we do the same kind of profiling experiment, this is a less clear-cut case, okay, and is maybe a little bit more typical. So Castep is a particularly good case for hybrid version. So for CoMD, so the important ones here are again the computation in dark blue. There's some MPI point-to-point time in orange. And if we analyze this further, this turns out to be mostly MPI waiting. So rather than actually doing the communication, this is waiting for MPI messages, and it's a symptom of load imbalance between the processes. Then we also have idle time, and we also have OpenMP wait time. So that is actually, so what's going on there? So that's actually load imbalance between threads. So what we see here in this case, as we increase the number of threads per MPI process, then the MPI point-to-point time disappears, but we gain some OpenMP wait time. So we actually end up transferring the load imbalance from between processes to between threads, and that's because this particular version of the code really doesn't make much attempt to do load balancing between threads. So there's definitely some potential scope for optimization there. And again, as we introduce more threads, we introduce some idle time while the MPI communication is going on. Again, this is all done outside of any of the OpenMP parallel regions. So while communication is happening, and there are also some other sequential bits and pieces in this code. So while those are happening, the other threads are idle doing nothing, and that red time starts to dominate or starts to become important. So again, in this case, it turns out that for this particular configuration, 4 threads per MPI process is best. Okay, so let's move on and talk a little bit about the accelerator support in OpenMP. So this part of OpenMP has taken a bit of time to develop, and part of the reason for that is that it's the way it's designed is that it's not supposed to be GPU specific. It's supposed to be more generally supportive of other accelerator devices. However, there aren't very many interesting ones around at the moment. So when this process was started in OpenMP, then the Intel Xeon Phi line of chips was sort of considered to be current and important as should be programmed as, or is intended to be programmed as an accelerator device. However, then they later changed their mind and said no, the Xeon Phis are actually the main chip, and you just run standard OpenMP on those. and then of course Intel canned the project altogether. So most of the interest these days is definitely focused on GPUs. There is the only other one I know of is a bit niche. So Texas Instruments have an OpenMP implementation that offloads to their DSP chips, but that's not really of interest to HPC users. So a design for OpenMP is fully integrated into the rest of OpenMP. Okay, so it's very clear how the offloading is supposed to interact with the multi-threaded capabilities of normal OpenMP for the multi-core CPU. So it's been developed over quite a few versions of OpenMP now. It came in 4.0. But there have been significant revisions and extensions in the later versions. So we're up to version 5.2 of OpenMP at the moment. So there's been sort of continual additions and some redesign of the accelerator features in OpenMP. In many ways, it's similar, but not the same as another standard for programming GPUs with directives, which is OpenACC. So that's an alternative. And it was actually developed before OpenMP 4.0, but it was really developed for GPUs only, and it isn't intended for other devices. In practice now, pretty much you can do pretty much everything in OpenACC that you can do in OpenMP 5.0 and later, and vice versa. And so the functionality between the two is pretty much equivalent. The details of the syntax and some of the semantics are a bit different, but the overall functionality is pretty much equivalent. And there's now quite a number of usable implementations of OpenMP for GPUs in different compilers. So, for example, NVIDIA, Cray, IBM, Clang, GCC, Intel all support to some extent, at least, the offloading capabilities of OpenMP in a reasonably robust and usable way. So how does this work for GPUs? Well, it's a somewhat higher level interface than, for example, CUDA or HIP. So it avoids some of the boilerplate code. The compiler and the runtime does quite a lot of the work for you versus having to code stuff explicitly in CUDA. That does sometimes come at some expense, that the performance may not be as good as what you can potentially achieve if you work hard with tuning your CUDA code. You might not be able to quite match that with OpenMP. But in lots of cases, it's and at least for fairly simple cases, the OpenMP performance is now pretty good. So it includes some constructs, the way it's designed, which I won't go into the details, but it includes the constructs that map to the hierarchical hardware on GPUs. So the GPU contains multiple SMs, and each of those runs multiple hardware threads. So the GPU hardware design has this kind of two-level hierarchy, and the OpenMP, the way OpenMP works, kind of matches that. So you can see that the way it works is that in OpenMP, so you start off executing on the host or the CPU device, and then at some point you offload, and it has this kind of hierarchical structure where you create a bunch of teams, so where each team has its own master thread, and then in turn each of those teams creates a separate parallel region, which behaves pretty much like the OpenMP parallel regions on the CPU. But between the different teams, there are some restrictions which to do with the fact that you can't synchronize threads that are in different teams. And that reflects the lack of synchronization capabilities in GPU hardware. Probably the most important thing really is that it's a vendor neutral API. So that's going forward in terms of software sustainability of software in these large applications and portability, then that's generally a good thing. So if we develop with OpenMP for GPUs, we have some reasonable expectation that it'll work on different GPU hardware with different compilers, etc., etc. And the other thing that's maybe worth noting is that in general it has better Fortran support than things like CUDA. So it has it supports more recent Fortran features, and is generally more easier to use for Fortran. So we go back to the example we had before of a double nested loop that is nicely parallel. Then suppose instead of wanting to execute that on multiple CPU cores, we wanted to offload that to the GPU. Then we can do that again with a single OpenMP directive. So I won't go into the details, but okay. So target means do the offload. Teams means create multiple teams on the GPU device. And then, so this is kind of a relatively recent feature in OpenMP. You can just say loop here, and that just basically asserts that all the loop iterations are independent, and leaves the details of how those loop iterations are mapped to the GPU hardware down to the compiler and the runtime. And it basically says, there's lots of independent iterations here. Go and map it how you see fit. And then we have to tell it something because the CPU and the GPU have different memory spaces. We basically have to specify what data we need moved around. So in this case, we need the arrays A and C need to be moved from the host onto the device at the beginning. And then the array B, which is the one being modified, needs to be copied onto the device, onto the GPU to begin with, and then copied back at the end. And the collapse to clause here, what that's saying is that that says, okay, actually it's not just the outer loop we want to parallelize, we want to exploit the parallelism that comes from both the I loop and the J loop here. So again, so simple minimalist example, and there's a lot more control is possible if you want to. And generally speaking, dealing with sort of arrays and multidimensional arrays as the data structures is fairly straightforward. If you have objects or in general user-defined data structures in your code, then the whole data transfer problem gets a little bit messier and more complicated. But there now are quite a lot of features in the OpenMP specification that allow you to deal with that. Some performance issues. Well, so this is not specific to OpenMP at all, but transferring, this is one of the big problems with programming GPUs, is that transferring data between the host and the device is expensive. Hopefully this is going to improve in some future hardware designs of GPUs, where we're going to start seeing unified memory between the CPU and the GPU. So some of these costs may reduce in the future, which will be a good thing. But for the time being, we need to minimize that as much as possible. In other words, don't transfer any data that's not needed and keep data on the device as far as possible. And OpenMP has this mechanism called target data regions, which allows us to manage the data transfers independently from offloading the computation. So it allows us to keep data on the device as much as possible. Another thing is that GPU need lots of threads or lots of parallelism to work efficiently. We need to typically expose a lot more parallelism. And for example, the example I've just shown, we use the collapse clause to exploit parallelism from more than just one loop in a nest to get enough parallelism to keep all our GPU threads busy. Okay, so the last topic I'm going to cover is something a little bit more speculative, and it's something that I've been working on over the last few years and looking at, and then that's to do with it's basically exploiting some features of OpenMP tasks. So in practice, most parallelism in scientific applications comes from parallel loops, and OpenMP handles those very well. But there are some other cases, so things like while loops, parallelism from recursion, functional parallelism, where we have, say, multiple function calls that can be executed concurrently, and also some types of parallelism where it's very irregular. So some pieces of computation take much longer than others, and parallelism is maybe nested as well, which gets difficult to exploit with just simple parallel loops. So OpenMP supports tasks. So a very brief introduction. So tasks are just independent units of work. It's a way just to identify independent pieces of computation, and essentially hand over all the responsibility for which thread does which tasks over to the OpenMP runtime. So it's a way of decoupling the specification of parallelism from the actual mapping to threads. So tasks are composed of two things, basically: a piece of code to execute and some data to compute with. So essentially we can have per task private copies of data items rather than per thread, which is what you'd have with normal OpenMP parallel regions and loops. And then the tasks are assigned to threads for execution. Somehow that's all essentially pretty opaque to the programmer. We don't really have very much control over that. Just have to trust that the runtime is going to do sensible stuff for us. So that's a useful feature, but OpenMP tasks are quite powerful because of particularly because of two features that they have. First one is that they can be nested. So a task may itself generate more tasks. So that turns out that it's really useful. It's more flexible than nested loops or nested teams of OpenMP threads if we have irregular and nested parallelism to deal with. The other powerful feature is that we can specify dependencies between tasks. So if the tasks are not all completely independent of each other, some of them need to be executed before others, then there's a mechanism to specify that. And what that enables is actually potentially is a coarse-grained data flow type programming style. So we can identify tasks and also the dependencies between them, and simply allow the runtime to figure out how to schedule those tasks and respect the dependencies. And that turns out to be really effective in some cases. Perhaps the most well-known or classical case where this is very helpful is things like dense linear algebra. So this is basically the mechanism that's used by the plasma library for dense linear algebra. Is to express everything as tasks with dependencies, and allow the runtime the freedom of how to schedule them. The question is, why might that be useful for exascale or large-scale processing? Well, one of the problems with scaling applications up to very large core counts is that for ease of implementation, a lot of applications actually have more synchronization than is really necessary. So for example, in OpenMP, you tend to have barriers at the end of the parallel loops. So you have lots of places where all the threads synchronize with each other, wait for each other to catch up, and then carry on computing. That's because that's an easy way to reason about the making sure that there aren't any race conditions and we don't have any parallel bugs in our code. But it's a source of inefficiency because it also causes, every time you have a barrier synchronization, that's also a potential place where load imbalance can happen if the threads arrive at that synchronization point at different times. And also a lot of applications also over-specify the order in which computations need to be done. So they, even in pure MPI implement applications, you often find that there's within each process there is within each process it's a sequential program. So there's a sequentially specified order in which things have to happen, which doesn't necessarily reflect any dependencies in the underlying algorithm. The other problem is that the MPI interface has support for overlapping of computation and communication. You can do non-blocking communication in MPI. In practice, this doesn't actually work very well. And the reason for that is that once the library as soon as the library returns control to the user program, the library then doesn't have any access to the compute resources that it needs to make progress in the background. So modern computer and chip and network designs mean that the network doesn't really have any capability to make much progress on the communications without involving the CPU. And this is quite a problem. So you can code your non-blocking MPI, but what you find is that basically nothing actually happens until you come to a blocking receive or an MPI wait, and then at that point all the communication happens, and you haven't achieved the overlapping that you wanted. So the idea that's here is basically if we could express all the parallelism as tasks with these data flow dependencies and include the MPI calls in that as well, we could actually potentially solve both of these problems. We could reduce or almost eliminate the number of barrier synchronizations that we need, and also get the overlapping of computation and communication really working properly. That would be nice, but unfortunately, if we just do that and hope for the best, then letting MPI calls happen out of order causes problems. You end up with potential problems with message mismatches and deadlocks and so on. So really, to make this tractable, you need a special MPI library. And there's a library called TAMPI, which stands for TaskAware MPI, which was developed at Barcelona Supercomputing Center, and integrate that with the tasking runtime, so that it handles things in a better way. And to be very brief here, the basic idea is that with this library, what happens is when an MPI call blocks, the task containing it is suspended. Okay, so as soon as an MPI stops waiting for something, waiting for a message to arrive, we suspend that task and go away and let that thread or core run other tasks. Could be other communications, could be other computation, and then only resume executing that task, that original task, when the message arrives. So it's a nice idea and allows this very sort of a large-scale data flow type approach to applications. Turns out it's not without the problems. It turns out that writing code like this is actually quite difficult, and debugging and performance and analysis is tricky because we don't really yet have the tools to support it. In any case, I've recently published a short introduction to this style of programming. It's a relatively short report, it's about 10 pages or so, but it gives you some, if you're interested in looking into this a bit further, then that's where this report is, and it also gives pointers to various other resources for this style of parallel programming. Okay, so I'm going to finish up as promised by very quickly saying, well, why use OpenMP and not some other API? Because there's enough of them. There's other things around. Well, essentially, really several reasons. Well, OpenMP is a mature, although still evolving standard, and it has a very robust standards process and very wide support from vendors and compiler implementers. So it's kind of it is probably the de facto standard for programming shared memory in at least in the sort of scientific HPC space anyway. But it's not perfect. So let's briefly consider what are the other options and why you might want to use them instead of OpenMP. So first of all, let's look at the alternative for programming for programming multi-core CPUs. Well, there's very old, tried and trusted POSIX threads or P threads. It's very widely available. It's an open standard. But it's rather lower level than OpenMP, so it lacks support for doing things like parallel loops or reductions or tasks, things which OpenMP handles really nicely for you. You can code it all yourself in P threads, but it's a bit more. It's a fairly bit. It works. It's a fairly bit more painful. Doesn't have a standard Fortran interface. C++ threads, okay, so threads are now built in as have been for a while as part of the C++ standard. Clearly that only works for if you have C++ code. And really the advantage of that is that it does have better integration with the latest features of C++ than OpenMP does. So there is there's always a lag between C++ adding features to the C++ language and getting those new features supported in the OpenMP specification. And that's actually quite a long lag there. It's kind of 5 years-ish at least. So if you want to use if you're keen to use the latest C++ features, then you might find that those don't necessarily work with OpenMP. The interface is a bit low level. It's a bit like it's a bit like an object-oriented version of P threads, and there's also some issues with it with control over threads. It doesn't really give you as much control over how many threads you have executing and exactly what's done by what thread, as you might hope or like in HPC situations. The TBB thread building blocks, again, that's C++ only. It's an Intel specific thing, but it does have some higher level features like OpenMP. So it's more sort of OpenMP like than C++ threads. And then finally, if we're thinking about doing hybrid programming, then an option we can't, that is there is to use MPI shared memory. Okay, so the MPI standard has a mechanism for actually, if you have MPI processes running on the same node, to actually create shared memory segments where, so that's pieces of data or part of the data where multiple MPI processes have access to the same data. So that's nice because it's then still just all MPI. You don't have to care about any of the interoperability issues or whether your OpenMP library is thread safe or not or anything like that. So that in some sense that's nice, but it has limited support for loop parallelism, for doing load balancing or anything that's sort of like tasks or anything like that. What about GPUs? Well, the most, because of the dominance of NVIDIA for the last goodness knows how many years in the GPU market, then CUDA has become a very widely used API for programming GPUs, and it's mature and robust. It's a little bit lower level than OpenMP, and it's okay. So, but most people can live with it just fine. It is sort of vendor specific, and it's and the Fortran support is perhaps not as good as you might like. But yeah, it's still very there's a lot of CUDA code out there, and it does work fine, as long as you're not super concerned about portability. That might be a perfectly good solution. There's also SYCL. So this is it now has an implementation from Intel called DP++. So again, this is C++ only. It is, however, an open standard. It's not as mature as OpenMP, and there's not many implementations out there. But it does integrate quite nicely with C++, and again, maybe works with newer C++ features than OpenMP does in some cases. We've got OpenCL. Okay, OpenCL is very low level. You really don't want to write that if you can avoid it. It is an open standard. There are also some so it's in principle very portable, but there are some questions about the performance and practice. The performance of OpenCL may not turn out to be as good as some of the other APIs. And then one that's already mentioned is OpenACC. So in spirit, it's very similar to OpenMP in terms that it uses it's all based on directives. It's actually a bit more mature than OpenMP. There are still maybe a few cases where OpenACC will give you better performance than OpenMP, but I think those are becoming increasingly rare as the OpenMP offloading implementations mature, and there are fewer implementations of OpenACC than there are of OpenMP these days. Okay, so quick summary. Yeah, OpenMP it's a well-established standard for shared memory and now for accelerator offload programming. The design of large-scale systems means that it definitely has a role to play for exascale computing, both for programming CPUs and GPUs. And OpenMP tasks are perhaps a potential useful feature, but that's definitely still work in progress. Okay, so that's the end of what I had to say. So I'll open up for questions now, and I'll pass back to Tim to handle the questions.
Perfect. Thank you very much, Mark. Yet, as Mark was just saying, a quick reminder to the audience: if you have any questions, then please navigate to the Ask the Staff a Question panel. That should be accessible via the question mark icon on your screen. That should hopefully look a little bit like this. And then you can go ahead and type your questions in there so that I can read them out to Mark for you. So I'm just going to give the audience a little while to kind of gather their thoughts and ask a few questions of my own. So first of all, this is perhaps a stupid question, but more just to make sure that I've actually got this right. So OpenMP is deployed per node where we have shared memory, whereas MPI or TAMP, that's operating across nodes at the level of the full supercomputer, right?
That's correct. Yeah, that's absolutely right, Tim. Yes. Yeah. So we can only use OpenMP within a node where we have the hardware support for shared memory. Yeah.
Understood. And so in that case, what is the barrier to entry for using OpenMP? How much work would be required to port an existing application to make use of that hybrid MPI OpenMP framework?
So generally speaking, OpenMP is easier, or at least less work to implement than MPI is. So you can at least to get something working, reasonably well. You may have to put a fair amount of effort into performance tuning, But the basics of getting loops parallelized is relatively straightforward compared to writing MPI. But as I kind of alluded to, once you've got this hybrid application, then trying to figure out, trying to do the performance analysis and figure out what's really going on is actually quite difficult. And it's, you have to explore quite carefully with profiling tools to really figure out what's going on and what's limiting the performance.
Right, understood. Thank you. We've already got quite a few questions coming in, which is a really good sign. So first of all, what do you think of the recent work, remote offloading support for OpenMP and cluster OpenMP programming?
Okay, so yeah, there's have been some work to try and extend OpenMP beyond a single shared memory node. I think that's what the questioner is asking here, and to provide OpenMP across an entire cluster. There's been lots of attempts to do this kind of thing over the years. There is some interesting work going on, but it's really hard to make this scalable. So you can get it to work for a small number of nodes, but it's they're trying to run OpenMP across an entire thousand, entire supercomputer with thousands of nodes is always going to be an absolutely huge challenge.
Sure.
Will never really be solved.
Right. And there's another question here, maybe vaguely related. This is from Michel Martone. Asks, hasn't OpenMP standard recently grown a bit too much, thus hindering a bit its learnability?
Yeah, that's a good point. I think that is a fair criticism. It is very big. I think that it's still the case that certainly if you're for a lot of applications, then the sort of the older parts of OpenMP are pretty much absolutely sufficient for what you need. Okay, so the basics of parallel regions and loop parallelism and basic synchronization mechanisms will cover a vast majority of the use cases for scientific codes. But no, it's a fair point, and I think in particular this standard has become a lot less. The standard document itself has become a lot less readable. It's had to develop a lot more terminology to make itself internally consistent, and that's made the text in the standard significantly more opaque. So it's kind of hard to pick it up and read about a particular feature and figure out how you're supposed to use it. So I think you probably now have to, or would want to, rely more on tutorial material to learn OpenMP rather than trying to pick it up by reading the standard, which I think was doable in the early days of OpenMP, but less so now.
I see. We've got two questions here from Jacek Dzidzic. First of all, for GPUs, how fast can OpenMP offloading get today compared to CUDA?
Well, this is one of these how long is a piece of string questions, but for reasonably simple cases, you can pretty much match CUDA performance. not in all cases. Now, there are cases where you can certainly do better by carefully tuning your CUDA code. You may be able to do a bit better, so reluctant to put numbers on it. But you often see, I've seen quite a lot of cases where you can certainly get within 20%, 30%, within 20% or 30% of the CUDA performance. So you're not losing that much.
Okay.
But I wouldn't complain. I wouldn't dare to claim that it's always going to give you as much performance as CUDA. But it's really not bad in a lot of cases these days.
Okay, thank you. And then the second question there was concerning hybrid, i.e. MPI plus OpenMP parallelism. I assume that MPI thread multiple, that is doing MPI comms from any OpenMP thread concurrently, is still very poorly supported. But has there been any progress in making MPI thread serialized, that is where any thread can do MPI comms, but only one at any given time, behave well in practice? Or do we still need to rely on MPI thread funneled, where only the master thread is allowed to do the MPI communications?
Yes. Okay. So there has been some progress. So MPI implementations have got a bit better. So and even the performance of MPI thread multiple has improved. So in practice, thread serialized tends to be okay. Because you are basically guaranteeing that only one thread at a time is going to be inside the MPI library, and that can be handled reasonably efficiently. In practice, not many applications do either of those. So in practice, most hybrid applications are still being written in the thread funneled, or even in the where the master thread is the only one that does the MPI comms. And that is partly for convenience reasons as well. Just turns out to be easier to do that without taking your application apart and refactoring it heavily. Yes, there has been some work on the on MPI implementations that has improved some of that stuff, but MPI thread multiple still is a problem. It's very hard to make MPI libraries thread safe and efficient, partly because they are old legacy libraries, and retrofitting they were never designed with thread safety in mind, and trying to retrofit it into them is really tough.
Right. We're getting quite a lot of questions through here, which is great news. So let me see, what should we go for? So here's a question for you. So if I get it correctly, OpenMP is meant to enable portable code, but what about performance? Is there any chance that we could run the same code on NVIDIA and AMD GPUs with a good performance based on the GPU specs? And is this a task of the compilers?
Okay, yes, okay. I think there is a fair chance now, actually, and I think this is, and this probably wasn't the case until relatively recently. I think you now do have a fair chance of getting, not just portability, but some reasonable performance portability. You might need still to tweak some of the OpenMP directives a bit towards specific hardware platforms. So it might not be the case that exactly the same code will give you the best performance on different, with different compilers and different hardware platforms. So you might still need to do some specialization of the OpenMP version for particular hardware platforms. But I think it's better than it used to be, and my expectation is it'll continue to improve.
Right, okay. And you also mentioned that OpenMP isn't GPU specific necessarily and can handle other accelerators, presumably things such as FPGAs and maybe in the future, hopefully
Well,
QPUs
maybe,
as well.
right?
But you know, like
FPGAs are always maybe in the future, right?
Sure. But you know, like in principle, does the way that OpenMP work vary significantly between different device architectures?
No, not really. As I say, I mean, it was the other implementations that were done or have been done were Intel Xeon Phis and or that I know of anyway, and Texas Instrument DSP chips.
Okay.
You can do, yeah. And actually, those actually they don't need this. They are not sort of hierarchy. They don't have this sort of two-level hierarchy that the GPUs have. So they actually don't need they don't really need some of the features that were put into OpenMP specifically to be able to handle GPUs.
Okay, I see.
But FPGAs are another matter.
Of course.
Yeah.
Well, I suppose going back to some of the questions from the audience here, one from Abid Malik. What is needed in OpenMP to handle extreme heterogeneity?
I'm not quite sure what the questioner is asking, is getting at with the extreme heterogeneity in there.
That's okay. We've got another question.
Sure. I mean, OpenMP so it kind of assumes you have a reasonably sort of symmetric computing environment. It sort of kind of assumes that all your cores are the same, and that if you have multiple devices, then they're all the same as well. Now, so if you can have multiple GPUs, but you can't have GPUs and some other device on the same node currently. So yeah, I mean, if you wanted to go that way, then you would need to there would need to be some additions to OpenMP, or at least extensions to implementations to handle that kind of thing.
Okay, thanks for that answer. And then there's one more question from the audience here. This is from Ivan Pribek. There have been some reports of a co-array Fortran implementation using OpenMP under the hood. Do you think that OpenMP is becoming a target/API for compiler implementers and less for manual parallelization by scientific programmers?
It clearly can be a target. So it's OpenMP is it can be used like that as a as a way of auto-generating parallelism for sure. And this is what's being a lot of domain-specific languages are doing that essentially. They have a higher level mechanism for describing parallelism, or the parallelism is kind of implicit in the domain-specific language, and OpenMP is used as the target for the DSL compiler to generate code against. So co-array Fortran, yeah, okay. You probably can do co-arrays on top of OpenMP, but that's not going to work in a distributed memory environment.
Right.
Yeah. So I guess you can. Yeah, you could. You could implement co-arrays for shared memory system on top of OpenMP. I guess that would work just fine, most likely. Yeah, so there are cases where where OpenMP is being auto-generated for sure, but I think still the largest use is as the sort of people are still writing a lot of OpenMP as well.
Yes. Okay. Well, that was the last question. I'm not seeing any more come in. We had a lot of very probing questions there, so you've done a commendable job giving very comprehensive answers to all of those. Thank you for that, Mark. So before we end, I think I'll just take a moment to plug CompBioMed's free scalability service. If you don't mind going on to the next slide for me, please, Mark. And one more. So if you are someone who uses or even develops biomedical applications that necessitate intensive computation, but you are running into performance issues that are limiting the scope of your research, then CompBioMed offers a service that's completely free of charge to improve the turnaround of your computing jobs. Next slide, please. So if that's something that applies to you and your research, then you can go ahead and fill out an application form available on the webpage displayed at the top of this screen. But otherwise, please feel free to reach out either at the email address shown here or via the In Silico World Slack channel. Next slide, please. So speaking of In Silico World, In Silico World is a community devoted exclusively to in silico medicine, offering expertise, opportunities for collaboration, and a safe space to exchange ideas and advice. Next slide, please, Mark. So already In Silico World has a large following, including members from large biomedical companies, biomedical SMEs, independent software vendors, clinical research institutions, and even regulatory and standardization bodies such as the FDA and NICE. So that's everything that I wanted to say briefly on the scalability service and In Silico World. I want to take this opportunity just to thank you once again, Mark, for giving us your time today. I found it a very interesting talk, and then there were lots of very insightful discussions at the end there in the Q&A as well. Just a reminder to the audience that this e-seminar will be available on the CompBioMed YouTube channel and website as well, if you wanted to go back over parts of today's talk, or if you wanted to view others in the series as well. So finally, thank you to everyone in the audience for attending, and I hope that you all enjoy the rest of your day.